Hello, welcome to another video from Module 1 of our Networking Fundamentals series. This module will teach you everything you need to understand how data flows through a network. This is part 3 of our lesson on routers, and in this video we will tie together some of the concepts we discussed back in lesson 1 with the concepts we just illustrated in the last few videos. In the last video, we showed you everything that happens to get a packet from host C to host A and then back. We showed you all the steps required for these two routers to hand data to one another. These routers happen to be deployed in a line, or linearly. But back in lesson 1, I showed you this topology and told you that routers are deployed in a hierarchy. And in this lesson, I want to show you why. Routers in a hierarchy allow topologies to scale much easier and provide more consistent connectivity for the users in the networks. So let me explain both of those points. Let's say the Tokyo network decides to expand and add two more networks, the accounting network and the help desk network. In each case, a router is stood up to handle the traffic for each of those networks, and that router is simply connected once into some sort of aggregation router, and instantly both of these networks now have connectivity into the rest of the topology of the Acme network. Hopefully this can show you that a network design where routers are deployed in a hierarchy is much easier to scale. To explain this second part, however, we're going to reconfigure these routers so that they are not deployed in a hierarchy and are instead deployed in a line, linearly. Notice now, if the sales team wants to speak to someone in the marketing team, they only have to cross 3 routers to get there. But if the sales team now needs to speak to someone on the help desk, they now need to cross 5 routers to get there. And this same effect actually happens in the reverse direction for traffic going to the internet. Notice the engineering team to speak to the internet only needs to cross 3 routers. But the accounting team, one of the new networks that we just added, needs to speak through 5 routers to get to the internet. So you can see that if you deploy your routers in a line like this, you don't have very consistent connectivity. The sales team is going to have a faster time getting to the internet than your help desk. Plus, if some sort of failure event happens at the marketing router, that happens to cut off access to the rest of the network for all the teams deployed after the marketing network. You don't have those problems if your routers are deployed in a hierarchy. If something were to occur to the marketing router here, no matter what, the accounting network and the help desk network is unaffected by that. Plus, for the sales team to speak to engineering, we have to cross 3 routers, or for the sales team to speak to the help desk, you still have to cross only 3 routers. And of course, in all cases, for any of these teams to speak to the internet, they just have to cross 2 routers. This makes for a much more consistent connectivity experience for the users in your network. So those are some reasons why you want to deploy routers in a hierarchy, because it allows for your topology to scale much easier and creates a more consistent connectivity experience for your users. Of course, routers being deployed in a hierarchy doesn't invalidate the illustration we did in the last video of packets flowing through linear routers. Because even if the routers are deployed in a hierarchy, the path between hosts flow through routers as if those routers were indeed linear. So our illustration from the last video, which showed you how routers pass data to one another, still absolutely applies. Host C from our previous example could absolutely be some host in the sales team of New York. And host A from our last video could absolutely be a host in the marketing team in Tokyo. All the routers in between form a linear path which data would flow through to travel between these two hosts. So these are 2 reasons why physically routers are typically deployed in hierarchical topologies. But there is still another reason which I'd like to unpack next, and that reason is that routers in a hierarchy allows for what's known as route summarization. To explain route summarization, let's focus on router 5 for a moment, and let's take a look at router 5's routing table. In the last few videos, we discussed that every router has a routing table, and that routing table is a map of every network that exists. In this topology, we have 6 networks, and router 5 is going to need a route for each one of them. There'll be 3 networks to account for the 3 teams in Tokyo, pointing to router 6, router 7, and router 8, respectively, and 3 more networks accounting for the teams in New York, each pointing to router 4. Now I want to quickly pause and talk about this /24 real quick. To explain it fully, we'd have to dive into the world of subnetting, which we're not going to do in this module. But I do want to give you a quick glimpse into that world to explain what the /24 means. When we say /24, We mean that these routes are going to match on the first 3 octets of a destination IP address. This /24 refers to the bits in the IP address. Remember back in lesson 1, I told you that an IP address is simply 32 bits, which we break up into chunks of 8 or 4 different octets, and we represent each of those octets as a decimal number. That's all an IP address is. And when we say /24, what we are saying is we're going to match on the first 24 bits. So there's 8 there, another 8 there, which brings us to 16, another 8 there, which brings us to 24, and that's what we mean when we say a /24 will match on the first 3 octets. In practice, the way it works is if a packet showed up to router 5 that looked like this, each of these routes would have router 5 look at the first 3 octets to find a match. 104077 matches this route right there, and this particular packet would be sent to router 8. And if this packet were to show up on router 5, again, router 5 would take a look at the first 3 octets to find a match, and a match would be found right there, and this particular packet would be sent to router 4. So that's what that /24 means. But notice in router 5's routing table, we have 3 routes all pointing to router 4, accounting for each of the 3 networks in the New York office. But everything at the New York office starts with 10.20. Well, what if we could simplify these 3 routes into a single route, telling router 5 to only look at the first 2 octet to find a match on 10.20? Well, we absolutely can by telling router 5 to match on a /16 network. If a /24 matched on the first 24 bits, then a /16 is going to match on the first 16 bits, which means the first 2 octets. This route is telling router 5 that any packet with a destination IP address that has a 10.20 in the first 2 octets should be sent to router 4, and then router 4 will hand it off to the next appropriate router in the path. So now, if router 5 received this packet, since we have 10.20 in the first octet, this packet would be sent to router 4 for delivery. Notice we were able to reduce the number of routes in our routing table. We went from 3 routes initially to just a single route. Now, it might not seem like a jump from 3 routes to 1 route is all that useful, but consider, what if the New York office scales? Here we only have 3 networks, but what if we added another 10 networks or 100 networks? Well, since they all belong to New York, they're all going to start with the 10.20 IP space, and router 5's routing table will not have to change. This one route will account for any additional network added to the New York IP space. So that's one of the benefits of route summarization, is that it reduces the routes in a routing table. But can we actually take it a step further? Let's take a look at router 8's routing table, and let's focus on that for a minute. Just like before, router 8 has to account for every single network in this particular topology. One of the networks router 8 is directly connected to. That's the 104077 network. Then router 8 will have 2 more routes for the other 2 teams in Tokyo, and 3 routes for the 3 teams in New York. Just like before, we could summarize these 3 /24 routes as a single /16 route, telling router 8 that to get to anything in the 10.20 network, send it to router 5. But take a look at where router 8 is in this particular topology. Notice that whether router 8 is speaking to New York or router 8 is speaking to something else in Tokyo, either way, the next hop in the path is going to be router 5. Which means we can actually go a step further than this /16 route. We can simply tell router 8 to send anything that starts with 10.whatever to router 5. This /8 is looking for a match in only the first octet, which means if a packet shows up that has a destination IP address of 10.whatever, router 8 is going to forward that packet to router 5. So that could be a destination host in Tokyo or a destination host in New York. But there's something I have to draw your attention to. What happens if this packet shows up on router 8? Well, this /8 route says we're only going to match on the first octet for a value of 10, which this packet does indeed match. And this /24 route says we're going to match on the first 3 octets of 1040.77, which this packet also matches. So you see this particular packet happens to match both of those routes. In such cases, the router has to make a decision upon which route to use to forward this packet. And the decision criteria that the router is going to use is which route is most specific. In this particular instance, a /24, since it matches more octets, is more specific than a /8, and therefore this packet will be forwarded using this route. Now there is much more to how routers decide which route to choose when multiple routes match. I created a separate video discussing it, and I'll add a link to that video in the description just below the like button. Either way, this is how router 8 would account for any IP address in the Acme Corporation IP space, whether it's in the Tokyo office or the New York office. But there's still something we have to account for, and that is every network that's going to exist out on the internet, of which there's going to be thousands and thousands. But again, notice where router 8 sits in this particular topology. To reach anything on the internet, router 8's next hop is always going to be router 5. So we can actually go a step further than using a /8, since router 8 needs to use router 5 regardless whether it's trying to speak to Tokyo, New York, or anything on the internet. To do so, we're going to give router 8 what's known as a default route. A default route is sort of like the ultimate route summary. It looks like this. It uses a /0 route. Just like a /24 matched on the first 3 octets, and a /16 matched on the first 2 octets, and a /8 matched on the first octet, a /0 would indeed match on 0 octets, which means every single IP address is matched by this particular route. This default route is essentially telling router 8 that to get to anything, go to router 5, which if you look at the topology that router 8 is deployed within, that is indeed the next path, whether it's speaking to Tokyo, New York, or anything out on the internet. For all packets that router 8 receives, whether they're destined to something in Tokyo, or destined to something in New York, or destined to something out on the internet, router 8 will use router 5 as the next hop in the path, and then router 5 will distribute it to the next hop as necessary. This is what I mean by a default route being sort of like the ultimate route summary. And that is our discussion of route summarization. And again, route summarization is only possible if you deploy your routers in a hierarchy. And that brings this lesson to a close. The main takeaway from this lesson is that routers are typically deployed in a hierarchy. This makes it easier for topologies to scale and allows for more consistent connectivity experience for the users in the network. Plus, the hierarchy allows for clever route summarization, which will reduce the number of routes you need in a routing table. And we also discussed the ultimate route summary known as the default route. And we gave you a brief glimpse into some subnetting concepts as we define what a /0, /8, /16, and /24 are. In the next lesson, we'll discuss the idea of networking protocols and introduce you to 8 common protocols used all over the internet. But that's it for our lesson on routers. I hope you enjoyed this video. I want to thank you for watching, and we'll see you in the next one. Hey YouTube, I hope you enjoyed that free lesson. I'm releasing this content for free to see how much interest there would be in a full Networking Fundamentals course taught in the same practical networking style. If you want the full course to be created, you have to help me out by spreading the word about this free module. If this content gets enough attention, I will definitely create the full course based upon your suggestions for what you want in a Networking Fundamentals course. Besides, I'm sure you know someone that would also benefit from learning how data flows through the internet, so you'd be helping them by sharing these videos. You could also further help me out with the YouTube algorithm by liking, subscribing, and leaving a comment below. I would appreciate it greatly, and I read and respond to every comment. Otherwise, feel free to join fellow learners and fans of practical networking on Discord. The invite is available at pragnet.net/discord. Thank you for watching, and we'll see you in the next video.